People probably are listening for me, huh?
I know.
All right, good morning. It is good to see you this morning. We have some special conditions going on for a little while until we get our air conditioning back, so you can thank the Lord for kind of a cool, breezy morning this morning. And we'll get to enjoy the sounds of the road going by outside and a few other odds and ends, but I think we'll still be okay. We'll just crank the sound system a little bit and we'll be fine. Well, this morning you guys are going to get the chance to hear a special presentation. Many of you know Tom and Betsy. They have been with us actually since the beginning, almost since the beginning. Yeah.
End of the summer over down on
By the harbor.
that storefront.
Yes. So we were going through pictures a little while ago, and we have pictures of Tom and Betsy helping us move from the original storefront we were in for only a year. So they've been with us for quite a while. But Tom and Betsy have some involvement in the intelligent design movement and have, I think, some really great stuff to offer us. So they have some presentations. So Tom and Betsy both have presentations. They both have, I think, some great connections here, and I've asked both of them to do a presentation for us on Sunday mornings. So Tom is going to get started. So you're going to get to see the first one, hear the first one today, and then, of course, we don't have Discipleship Hour next week because we're getting prepped for the big outreach for Independence Day. But then the following week, Betsy is going to do her presentation. So I think that one is The Tiny City, about the complexity of the cell and how it proves for us the fact that it was created by God. So Tom's going to get us started today. So let's just have a word of prayer, and then, Tom, you can come and get going. Father, we're grateful for your mercy and your grace, and we thank you, Lord, for the abundant evidence of your wisdom and power that is available to us through your creation. And, Lord, as Tom speaks to us today, Lord, strengthen and encourage our faith and help us to see more about your eternal power and Godhead. As we look at these truths this morning, Lord, we thank you for people who are willing to share your truth with us. And Lord, help Tom as he speaks this morning, Lord. Work in him and through him. In Jesus' name, amen.
Thank you, Pastor Ray. Betsy and I are driven to do this. It's kind of our training. Betsy's a biostatistician, I'm an engineer, and so we're kind of called to talk about these kind of things. And again, for those who aren't familiar with intelligent design, the concept is God's handiwork, like it says in the King James. I like that word handiwork because it talks about his construction, that it's intended to put together a certain way. And you see that mentioned in Romans 1, see it in Psalms. So think about it's designed that way, and no one's without an excuse. And people have to realize that. So people who say there's no God, there's no design, are lying. They're forcing themselves not to see what's there. And so hopefully you'll be able to see this presentation clearly from every direction and follow along. I'm doing this one on Privileged Planet. Normally we do biology ones, but this one is cosmology. So we'll start moving right through this one. It's a summary of a couple books that you could find out there. The first one is The Privileged Planet by Gonzalez and Richards. Second one is by Overman. Those two books give you a lot of the material I'm doing here from the Christian side, but also I'm going to be talking about some of the secular side as well, because that's what you hear on Nova. That's what you hear Carl Sagan talking about. He is not seeing the Christian side. He's not seeing the design side. Our outline we're going to cover in 4 areas. The first one I'm going to talk about is what's known as the Copernican principle, and also principle of mediocrity. Those are corrupted phrases. Copernicus was a very religious person. He was a a member of the church. He definitely believed in the leadership of God, but now the concept's been corrupted. So we're going to see it starts with Copernicus and then leads elsewhere. The first, we're going to go back 2,000 years to the time of Aristotle and Ptolemy and look at what they talked about. The concept there, we can move ahead to the earth is motionless. That was how Aristotle looked at things. And that makes a lot of sense. So if you look around you, we're not moving. The earth is stationary. I don't feel any wind. Well, today you feel the wind blowing, but in terms of the stars and the planets moving, the sun moving, we're stationary. It must be that way, so everything around there is revolving about us. Well, if everything is revolving and we're stationary, the heavens are moving. So there's now celestial spheres where the stars move at one rate, the sun moves at another rate, the moon is different than the sun. It's very complicated. Basically, they thought the stars rotated together. So there's like a layer. There's a sun layer, a moon layer, a star layer moving in the heavens. But it's more complicated than that because some planets move at different rates. Even back then, they realized that Venus and Mercury move different, faster than the other planets. Also, they sometimes move backward. How can that be? Well, other early viewpoints by some of the philosophers looked at some of those aspects. So we had another famous name we think of as Pythagoras. He had a viewpoint that the earth is a sphere. Now, of course, that brings question, if the earth is a sphere, what's it sitting on? How can it be just someplace there? We know things fall. But he's came up with the idea of the earth is a sphere, and that was, the Greeks were very clever. They came up with different experiments to do that. And one of the things they did is they'd put a pole up and they'd hang something down and look at it. And you can tell when the pole is straight up because whatever's hanging is right aligned there, like a plumb bob. Also, they dug pits or wells, and you could look down in a well and see where the sun is. Well, they did this at different latitudes. They'd go 100, 200 miles north or south and do the same thing with the pole and with the well. And they realized on the same day, the sun would be at a different angle. So the earth was not flat. There's a lot of people, they thought the earth was flat. Well, maybe some barbarians thought the earth was flat, but the people who really thought about things, we'll call them kind of the scientists at the time, realized that the earth was curved. And so Pythagoras thought, okay, it's a sphere, but not everyone did that. Another famous philosopher, Plato, thought the earth was a cube. They thought in terms of simple geometrical solids. You know, there's certain ideal shapes of things. Socrates said the earth was spherical and in the middle of the heavens, so it's somewhere hung up there supported by some unknown way. And he thought that what we know about the earth is just kind of hollows inside that. And last one I'm going to mention is Aristarchus. He's the one who said the earth rotates on its axis around the sun, and that explained the strange motions of Mercury and Venus. So that's kind of where it was, but Aristarchus kind of got lost because most people went with the views of Aristotle. Obviously, Aristotle is a pretty smart guy and very well known and did a lot of other leading things. So the status of the world as of about 1500 was the lack of wind was very compelling. The earth is stationary and we're not moving. Yet, why do Mercury and Venus move backwards at a certain time? People would make a model of the universe. They'd make so here's the earth stationary, and you've got planets, you've got sun, you've got the moon, and they had to come up with mechanical devices, very complicated mechanical devices to make things move backward at certain times. And one of the clever things they came up with was equants and epicycles. I don't know if you ever heard those terms, but the epicycle is a circle. Okay, think of a train, an old locomotive, old steam locomotive, and you're on the locomotive and you're looking at the driving wheels moving. You see the wheel going round and round and round. But if you're on the ground looking at the driving wheel, there's a flange on the locomotive that keeps the wheel on the track. It's a piece sticking down so this train doesn't slide off. Those of you who had model trains, you know what the flange is. You put it on there and it doesn't slide off sideways. Imagine a bigger flange, and now watch the train wheel coming around. As the train wheel comes down and sits on the rail, the flange is sticking down below it and actually moves backward when the train is moving forward. So from the train, you see the wheel going around. If you would look at a point on the flange from the side, you'd see it come down and then move backward and forward. You'll have to take my word for it, or go back and look at your model trains and figure how this works. Very complicated, and of course you don't want something that complicated. And that's where we really get back to the Copernicus coming in next. So Copernicus was the famous name. We realize that he's the one who really came up with the start of that. He said the sun is our basis of motion. The planetary motion is in reference to the sun. The Earth rotates. Now, they didn't understand gravity yet, but the Earth is moving around there, and it's moving around the sun. Now, that was very compelling because now it explained Venus and Mercury. He wrote these things in a simple manuscript that was circulated in the 1500s, but the main main manuscript wasn't published till after his death. Because it was kind of heretical, because most people said the Earth is not the center, or the Earth is the center, not the sun the center. And I thought this a very revealing quote. He said, "How astonishing if within the space of 24 hours the vast universe should rotate rather than its least point." Kind of goes back to Occam's razor of the simple explanation is the best. But he was still in the minority. That was compelling to some, but everyone else said, no, there's no wind. The Earth is not moving. We're stationary. That's where Galileo comes on the scene. He, along with Copernicus, took this viewpoint that the Earth was moving. Also, he and Copernicus differed from the Greeks. The Greeks were great philosophers, but they had some viewpoints that we would not agree with today. They thought time was kind of an illusion, where Galileo, Copernicus, and some of the other people saying was, no, time is fundamental. It's something real that happens. Also, manual labor is enabling. The concept in the Bible of man is made to work, that's good, where the Greeks said, no, manual labor is bad, that's something just for slaves. They were more into thinking about things. And also, if you know back at the time of the Greeks, there was a lot of pagan worship. You were worshiping the gods and nature, Mother Earth concept. Copernicus and Galileo went against that. They were both believing in God in the Bible. Galileo's a great scientist. He made contributions in astronomy and physics, engineering, and we hear about his conflict with the church. That's kind of what's famous, that the church persecuted him because of his beliefs that the Earth was not stationary. Actually, when you look at the study, he kind of precipitated that because he was a little arrogant. He would actually have fought back, and he published a paper that made fun of the Pope and pushed against that. And of course, the church is pushing back. So a lot of this conflict between Galileo and the church was caused by Galileo. Okay, after that, we find out what's happened. The world is kind of shifting as it becomes more scientific. It's becoming more secular and moving back almost kind of the Greek concepts of immaterialism and philosophy. People are moving away from a tie to the land and a belief in God and seeing God's hand in nature. And they're now looking at this godless view that things just happen. It started really, and they put it into the Copernican principle. I think they've corrupted Copernicus' love of God and view of God. Now, if Earth is not the center and we are just one thing moving around, the world, the universe doesn't move around us. We're just a small part of it. Now, that went further into the principle of mediocrity, because now, if we're not the center and not moving there, now there's all these other galaxies that we've learned about. We're just kind of insignificant. And of course, that's what Carl Sagan would say. And that was reinforced by Hubble's work with telescope, where these little fuzzy spots they saw in the sky are not just fuzzy gas clouds, but those are other galaxies. So now we've got billions of stars within one galaxy, billions of other galaxies. We are insignificant. And so that was the secular view that was promoted, which is obviously in conflict to the hundreds of year old church view. They actually came up with an equation called the Drake equation. This scientifically calculates the number of other people that are out there that we can communicate with. How many other, let me just jump ahead and put your mind on science fiction. You know, we see Star Trek, Star Wars, there's all these other people out there. Early Star Wars and Star Trek was very similar to us. You know, they just paint their faces and put hair on them and feathers or whatever. Now they got more sophisticated, imagining what other people are like. This is a way of calculating who's out there. So in that equation, each of those things are the number of civilizations that we can communicate with is each of these terms. So N is the number of civilizations we can communicate with, which should show up in the next line there. And then each of these terms, we'll go through them pretty fast. The mean rate of star formation, the fraction of stars with planet, the mean number of planets that can support life, the fraction of planets where life develops, fraction of intelligent planets that could communicate, and the length of time they're in existence. There's a scientific way of counting how many other people are out there. Carl Sagan's kind of view of billions of stars, millions of civilizations. However, if you look at the bottom, this is perhaps the equation that has the greatest uncertainty. The bottom end is 1. Well, it's us. It is 1. But Carl Sagan had a number up in millions. And it's really, how do you put numbers to these terms? The implications of this, that's why Carl Sagan thought there would be, next slide. Carl Sagan said there's millions of people out there. We just haven't communicated with them. The universe is populated by innumerable Earth and possibly innumerable forms of life. That is in the book, The Privileged Planet. It's also in a video, The Privileged Planet, or a quote from Robert Jastrow. And that's why we search for extraterrestrial planets. Why there's a search out there looking for nearby stars for planets. Also, we search for extraterrestrial intelligence by radio waves. That's what SETI has been doing for a number of years. We're fascinated by science fiction, and we realize that maybe 10 to 15% of books sales are science fiction books. There's a huge number out there, and of course a lot of science fiction movies on TV. But there's a problem. Enrico Fermi, the great physicist, really pointed it out at the bottom here. Where is everybody? There's people who claim, well, there's UFOs. Well, that is still, some people are convinced there are, and some people there aren't. It's not irrefutable evidence. So there's a problem out there. Next step on this is they put this together into the weak anthropic principle. We don't need God. We're here So all these conditions around us must be the way they are. I mean, if they weren't that way, we couldn't be here. It's just obvious. It's running the whole thing backward rather than trying to understand why and look for the source of the way it is. It's like, that's the way it is. It's easy. But if you don't have a base of comparison, if you haven't looked at other ways of doing it, haven't really been to other planets, it's, of course, this is the way it is. Now, that is the secular view. We kind of set that basis, but is there fine-tuning? Is there intelligent design that made it the way it is? That's the real question. How did it get to be that way? And so we're going to compare Earth to what we know about other planets and other features, and the features on Earth that make it very amenable to life, in fact, critical for life to exist. So that takes us to the next section of outline, which is the unusual features of Earth. First of all, we cover water. Water is a very unusual chemical. It has extremely high heat capacity that moderates temperature. Those of us who live near Lake Michigan know that by the lake shore it's very cool in early summer, but it's warm in early winter. That lake is holding a lot of heat, and if it wasn't for that, you might as well move to Nebraska, and you'll find out how the temperature swings even more and more extreme. But even there, they've got rivers and lakes to moderate it some. The water supports the largest creatures on Earth. Can you imagine a whale kind of moving around on its flippers? It would have to be constructed entirely differently. Its bones and structure are just not possible to do that. It's soluble for a lot of materials in there. For example, oxygen and carbon dioxide are soluble in water in different ways. Our bloodstream, both oxygen and carbon dioxide, that's our body's taking oxygen into our cells, and it's taking carbon dioxide back out to the atmosphere. Inside the oceans and lakes, we've got plants growing because the oxygen is traveling out of the plants through photosynthesis. It's taking the carbon dioxide in, so the water has both carbon dioxide and oxygen. During the day, the plants are making oxygen from carbon dioxide. During the night, it runs backward a little bit. It's excellent media for chemical reaction. When you see a chemistry lab on TV, it always has a lot of beakers with liquid of water, typically water. It has a very high surface tension. That is extremely important because the way sap moves up in a tree is through this surface tension thing. And of course, if it wasn't for that surface tension, we wouldn't have trees, and then we wouldn't have maple syrup. So think about the problems that we'd have if we didn't have that. Water goes into air as a vapor, and that's what makes rain. It's a solid that floats. 99.9% of solids sink. If water forming ice did not float, the ice would go to the bottom, and every summer Lake Michigan would be about a foot deep with water on the top. No fish, no plant life in there. And then in winter it would freeze solid again. Another point, it seems to facilitate tectonic motion. And that's an important thing in Earth as far as things moving and recycling. It's transparent to light. Well, obviously it has to be, or else we wouldn't have sea creatures and plants below the surface. They'd only be like lily pads sitting on the surface. Next one is quenches fire. We'd be in big trouble if we didn't have fire departments with water. And the last one I mentioned is low viscosity. That's kind of tied into that blood aspect, but blood is circulating through us. If blood was really thick, if it was like 90 weight gear lubricant oil, we couldn't circulate the blood through our system. So all these factors are critical. Next, I want to look at the balance between land and water. If we had too much land, there'd be no water cycle. Everything would just be land. We got to have the water with it. On the other hand, if it's all water, we couldn't mine for minerals. It would hard to make technological progress. How would you have fires and things like that? If you go to parts of the earth where the balance has changed a little bit, you'll see some of these things. Alpine Tundra is not very fertile. It's very limited. It's a very small number of plants because it's very cold, or because it's high, so it's cooler up there. Likewise, Arctic Tundra. You don't see a lot of plants growing up there because it's cold so much it doesn't grow. And then deserts, there we see the lack of moisture. Next thing we want to look at is the importance of other aspects. The moon. A large, close moon causes large tides. Now, even here, there is a tide in Lake Michigan, a small tide, but obviously the ocean is more extreme. That contributes to ocean currents. It keeps north latitudes warm. Like if you look at where Great Britain is, it lines up with Upper Canada. If you didn't have the Gulf Stream going up there, Great Britain would be like northern Saskatchewan. It mixes nutrients and it allows life in a tidal zone. So you've got air, you've got water mixing back and forth. Also, the moon shields the Earth from some impact events. We see craters on the moon. How do they form? Those are impact events. If the moon wasn't there, maybe whatever caused those impacts would hit the Earth. Another aspect of this is comparing the moon and our axis of rotation. Our moon is unusually large compared to the size of the Earth, and that stabilizes with the orbital gravitational mechanics, the rotation of the Earth. Mars moons are much smaller, and also because of that, it's not stabilized, so its axis swings around a lot more. Our Earth has a tilt. That tilt is very important as it precesses around, and that gives us seasons. If it wasn't for that, it would be very stably, very hot at the equator and very cool at the poles. Without the tilt, we would have no rainy seasons moving around. Okay, what's the situation with other planets in the solar system? They have the wrong light intensity. The amount of sun hitting the surface or energy hitting the surface of the planet is a function of the square of the distance from the sun. Mercury and Venus are very close. They're very hot. On the other hand, you go further out, the closest in environment would be Mars, but Mars is extremely cold. And as you go out, it gets worse and worse. We're kind of in the Goldilocks range of water. So if there was water on Mercury, it would just be as vapor. Any water on Mars would be as snow. And they're looking for that, see if they can find that. The other planets do not have a breathable atmosphere, at least what we would think. I guess if you could breathe methane, you could live on some of those other planets. Some of them have very strange tilts, and so there's season. I think it's Uranus is like near 90 degrees. It's very unusual, and so it's pointed out there. They don't have a precession of axis, so their climates would be very extreme. Most of the other planets have gravity that's too high or too low for the way we have life. You'd have to redesign life entirely. They don't have magnetic shielding. That's very important because our magnosphere keeps a lot of the cosmic rays from hitting Earth. Otherwise, our ultraviolet intensity would be much higher. And of course, our atmosphere helps with that as well. And also, a lot of these planets do not have our balance of minerals and metals, which are important for our technology. If you were on a metal-poor planet, you couldn't make metal tools and utensils, which, ubiquitous, are chair legs, building frames, cars. Now, they've been searching for other planets, what are called exoplanets. And it's pretty clever how they do that. They look at stars, nearby stars, and one way is measuring light intensity. Once in a while, the light intensity will take a drop, and that's interpreted as a planet going in front of that star, so it gets dimmer. Another way is they look at the motion of it, and once in a while it wobbles a little bit, and that also is attributed to motion, gravity pulling it ahead and behind. This is the 5,000 planets that they have identified in nearby stars. And I put a green circle here. That's at 1 Earth mass and 365 days. So try and imagine what life would be on one of these other planets, totally independent of whether it's oxygen or water or the right temperature or anything else. Imagine orbit period of less than a day. That means you're going around the sun every day. On the other hand, it's 100,000 days. So you'd never have a birthday. No cake on those planets. On the other hand, look at their mass. At 0.1 mass, 0.1 of our mass, you have basically no gravity. It's like the bouncing on the moon. How could you imagine life? On the other hand, imagine a planet with 1,000 times our gravity. It's impossible to imagine any kind of life there, even in water, like an amoeba or something like that. How could that happen? So the possible life would be a small circle around that. Like, quick go to resources on Earth. What else do we have? And so the next thing we're going to talk about is elements on Earth, and we'll go through this list quick. When people look at the human body, we know we have certain things in there. We know we need hydrogen, oxygen for water. We need carbon and hydrogen for the hydrocarbons, amino acids. We know, if you studied a little bit about blood and hemoglobin, you got to have iron in there. You need to have magnesium. Why do we take vitamin pills? There's all these things in there that list. And so there's about 27 essential elements that are in the human body. We've got them all. They're here. Let's go to the next slide, which is talking about plant reservoirs. Stored plant reservoirs are so essential to our way of life. Wood is stable for hundreds of years, especially if you go to alpine areas, like if you go in the Rocky Mountains, there's wood that's hundreds of years old that hasn't rotted or decayed because termites can't live up there. We make buildings out of that, so there's 100-year-old buildings where wood is stable. Coal, next one, fueled the Industrial Revolution. Natural gas heats most of our houses, and petroleum is key to us because we used a lot of that this morning getting here with gasoline, diesel, goes into plastics. If we didn't have other petroleum deposits, we wouldn't have asphalt for our roads. We'd have gravel roads or very muddy things. So the stored hydrocarbon is very important to us. They're critical to our way of life. Let's go to the next slide. Go back 200 years ago, we had candles, oil lamps, torches. It'd be difficult to imagine our lives today with them. Wood and charcoal heated the first refining of metals. Try and imagine without aluminum pots, without copper, without iron, how important that is. The fuels can reduce calcium carbonate, which allows us to make cement. Stable storage of plants and grains allow feeding over winter. If we didn't have stable hydrocarbons, and we would not have carbohydrates, we would not have our winter wheat. Let's talk about the core of the Earth. The core anchors that magnetic field. It's like a motor. It's a dynamo with circulating current in there, and that makes that shielding. The radioactive heating keeps it molten, and there's a lot of planets that do not have a molten core. In fact, the majority don't. The lower density are oxides that are on the surface. That's what form the Earth crust. And the tectonic plate activity allows things to move around, circulate, kind of recycles things that we have. The mass of the Earth has a major influence on the size of the life, which goes back to the exoplanet idea. If we had too little mass, not only would we be bouncing off the surface, but we'd have very little atmosphere. If we had too much, we would have excessive atmosphere. That would limit the light getting down to the surface. And if we had cloudy layers, we'd have no knowledge of cosmology. We'd have no understanding about the sun and stars. Okay, do we need it that way? Can we have life without all of these different factors? In science fiction, sometimes you hear about life based on silicon. But if you really look at the details, the number of compounds, there used to be a handbook of physics and chemistry listed organic materials which are based on carbon. That is 10 times greater than all the others together. There just are not enough silicon compounds, and they're not suitable with their linkages for life. Other elements would even be poor bases for life. So it really depends very much on carbon and the carbon-hydrogen bonds, which we don't have time to go into. We'll go on to the next section, which is the circumstellar habitable zone. That means the area around the sun in which we can live. Earth is in a very stable, uniform orbit. That means it doesn't get much closer to the sun as it moves around. Also, the sun's output is very stable. It doesn't have to be that way. A lot of stars are variable. In fact, there's something called Cepheid variables that are very extreme. So if the sun would pulse its energy, it would get too hot and too cold. Also, we're at the appropriate distance from that sun. As I mentioned, if you're very far in, it'd be too hot if you're too far out. If the sun had a different output, and they vary by more than a factor of 20. So some suns are way too hot. Just because you've got a planet out there, it may be cooking or it may be all frozen in another environment. The output of the wavelength of light is just what we need for photosynthesis and seeing. Now you can go the opposite way, the secular view, and say, well, of course it's that way. It couldn't be any other way. We adapted to it. So you can look at that argument both ways, but you really should say, boy, that is amazing coincidence. That is really unusual. Next comment about Venus, 900 Fahrenheit. And Mars' atmosphere is 1%. Those are the two closest planets, and look how extreme differently they are. Other planets are even more extreme and inhospitable to life. Also, those outer planets are catching any asteroids and comets that are coming through, so there's a lot more impacts there. That really comes down to the fact that we're at a special intermediate location in the solar system, but we're also in the galaxy. It's important. The Milky Way, we've seen pictures of all the stars and the arms. Well, the inner region is thought to have a massive black hole. And as things go into the black hole, they emit a lot of X-rays. So if we were closer to the center, we'd have too many X-rays. We could not exist. Also, it has more supernovas. I mean, that's pretty obvious. That sounds bad. We don't want to be around too many supernovas. The outer regions are low in the metals needed for life. And also, we're in between the spiral arms. So again, it's a little more open, appropriate area. So let's try and put this together and see how this fits. These are amazing coincidences. Let's try and total these up and think about what this means. Number one, we have a stable sun. If it was going through variation, we just couldn't exist. We have the proper amount of metals. If our if the planet was all nickel or iron, we wouldn't have appropriate carbon for plants and such. On the other hand, if it was all carbon, we couldn't have the metals that our civilization really depends on. Also, we need other elements that listed 27 for our bodies. We have them in appropriate amounts. They're there. We have the right size planet. We have the right temperature range. We have a large moon that gives rotational stability. Circular orbit, the proper tilt, optimal solar spectrum, tectonic plates, the magnetic core for the shielding, optimal atmosphere, water-land balance, so we get the right amount of rain but still have enough land that we can grow crops. We have these fuels that have built up from the past. If we didn't have, imagine if we only had wood. What would life be like? How would you take wood and put fuel? Everyone would have their own wood lot because you'd have to heat your house with your wood lot. You'd saw it by hand. It'd be a very difficult life. What if we didn't have trees? What if the gravity was so high we couldn't have trees and all we had was grass? How can you imagine heating your house, and what would you build your house out of? We have concentrated ores that allow us to do metallurgy and make steel and aluminum. More coincidences. Life needs a habitable planet, but life is what makes a planet habitable. This is a very interesting concept, because if we were going, Star Trek, going somewhere and finding another planet, and let's say there was no life on that planet, but if we were going to put life on that planet, what would we need? We'd need water. We'd need some oxygen for us to be there. We would need carbon dioxide to the plants to grow. All of these things are what our systems recycle. The whole Earth system recycles these materials and produces it. You cannot imagine going somewhere and finding an empty planet that was ready for life. There's no process to stabilize it. Everything is closed loop control that makes it work. The weak nuclear force is critically balanced between neutrons decaying too quickly and all hydrogen used up. So this is a physics point of view of how things are set up, how atomic reactions and such are balanced to allow things to happen. Next one down there. If the force of gravity were changed by 1 part in 10 to the 40th, that's 1 with 40 zeros after it, all stars would either be blue giants or red dwarfs. Just have to accept that because you have to be astrophysicists to do that calculation. I'm just going to take that number at face value and say they knew it and they got it right. Next one, the number of electrons must be balanced to that of protons to within 1 part in 10 to the 37. Again, 37 zeros over there. Or else electromagnetic force would overcome gravity. That would be, our planet would be more positive than the moon, and it would pull themselves together. If the electromagnetic force between those planets would pull things together, and we wouldn't have stable orbits. Right now, gravity kind of controls things. And the people who said, well, how could this all come together? How could this form? They said, a black hole cosmos is much more likely than ours by a factor of 10 to the 300. That's, in other words, all these subatomic forces are balanced correctly to have it that way without us collapsing into a black hole. Okay, let's go back and look at the Drake equation again. Remember all these numbers? Let's just bounce down all the way through them. The first maybe 4 numbers are really easy to come up with. Astronomers can do that. But look down to NE, the number of planets that could support life per star. That is probably one of the greatest uncertainty. Carl Sagan took maybe 1 in a million. I think from a Christian viewpoint, based on all these coincidences here, you'd have to say 1 in a trillion, or 1 in 100 trillion, or 1 in a, I don't know what number you like, Googleplex. It's an amazingly large number. Perhaps the estimates would be lower if they considered these coincidences that we're talking about, the design for life. So the next slide really sums this up pretty well. A common sense interpretation of the facts suggests that a super intellect has monkeyed with physics as well as chemistry and biology, and there are no blind forces worth speaking about in nature. That's Fred Hoyle. He's the one who named the Big Bang because he believed in an infinitely long, stable universe. He could not imagine a start of the universe, and he said, this is crazy start. That's why he named it Big Bang, as being kind of impossible. He was not a Christian at all, but he was a very honest scientist, and he said, it can't just happen that way. There has to be some driving force behind it. Okay, well, let me show you some acknowledgements and references. You can come up and see me later, but basically I'd mention up front the privileged planet and the case against accident and self-organization. If you want to read more, those books are out there. And of course, from the secular side, I've got good, well-known encyclopedia there. Okay, next slide says, here's my bottom line conclusion. Random chance does not reasonably explain Earth's features. What you hear Carl Sagan saying, what Neil deGrasse Tyson says, they are fooling themselves. They're totally overlooking the concept of Romans and Psalms, that God's handiwork is out there, and they have rejected that handiwork, and I just want to point it out to you. Let's just go to the next slide, which is an open-ended question. I want you to think about this. Does have impact in your life or implications? You know, if you like science fiction and you read it, you say, yeah, that seems reasonable, or you really critically look at it and say, how can this be? This is so far against reality. And other things, when you're talking to other people and they're talking about, well, what are we going to find with SETI? What are they going to find on other planets? Let's search out somewhere. I think it's pretty much wasted money. It's so unlikely to find something out there, I just can't imagine it. So that's what I'll leave you with, just hopefully a huge picture of how special Earth is. Thanks.
All right, thanks, Tom. There's a lot of information in that, isn't there? But when you really stop and look at all of these factors, it just is amazing. And we are so blessed that we have a benevolent God who loves us and cares for us and has made a place for us, that we can not only live on a planet where life can just barely make it, but where we can have a wonderful, blessed life and walk with the God who did all of this. So thanks, Tom. So we'll hear in 2 weeks from Betsy about, so this is a big look, right? So if you want to kind of look at the universe as a whole and how it points to the fact that it can only be here because God made it, let's go ahead and instead of looking at the telescope, let's look at the microscope and let's see it from the other side, because from the very big to the very small, the whole universe is screaming, God made you, and he loves you. And of course, as we read the scriptures, he gave himself for you. So we'll take a break, and then we'll gather for worship here in just a few minutes.